Hi everyone, thank you for joining us today to the third IEEE IES webinar in 2022. Our speaker today, Terry, is from General MicroGrids, talking about the application of utility scale DER management for the DSO and embedded microgrids. Terry is a global energy expert using smart grid and renewable energy generation to address energy poverty and industrial energy reliability. He is currently the CEO of General MicroGrids, a global end-to-end solution provider for renewable energy technologies and transformational microgrid development. He was a founding member of the International Microgrid Association. He also was previously contracting general manager of advanced developments at Horizon Power. Terry, I think we can start. And everyone, if you have a question, please hold it to the end if you can. Then we have 15 to 20 minutes Q&A at the end. Thank you.
Great. Thanks a lot for the introduction. Let me pull up my slides here. Please let me know if you can see my screen. Can you see this okay?
Not yet.
No, not yet.
Says here it's presenting. Okay. I will transfer to a different application.
Yeah. Now we can see it.
Okay. I put this on full screen. There we go. So as introduced, I have previously worked with Horizon Power. I have probably close to 20 years, a little over 20 years in the energy sector. In North America, I work for one of the largest distribution network companies, electric network companies and gas company. And I've been working with advanced distribution systems probably my entire career. Today, this talk is going to be about technology that's evolved over the past 7 to 10 years and has become very mature. The description of what I'm about to provide for you has to do with some of my experience in deploying these systems. And we'll talk a little bit later about future capabilities that we see arising. I know it was in the title of the talk, talking about DSO. I'll be talking about DSOs just a little bit later. Anyway, I'll just dive right into it. DERMS technology is based on the fact that DER, distributed energy resources, are prevalent, not just in Australia, but they are around the world. As you can imagine, consumers are taking responsibility for generating their own power. And I'm going to be describing a technology that helps solve the imbalances coming from customer-owned generation that can be applied worldwide. So this is not just something that we see being deployed here. I'll also briefly speak about one of the deployments that took place in Horizon Power. Anyway, you can see that quite a number of organizations have decided to coin the term DER, has a range of meanings, but essentially what it is they're resources that are not necessarily large scale. They tend to be smaller scale, under 5 megawatts, and many of them are in the kilowatt range. But there's one other aspect to DER that people don't talk much about in Australia, and that's demand reduction or demand response. DER has DR, demand response, as a means in which to help balance a lot of the challenges that are coming from supply side. So if we look at DER evolution over time, this is a graph put together by one of my colleagues in the United States, talking about how we see over time that there's going to be much more higher penetration and higher density of DER adoption, not only by the consumer, but many utilities are starting to install neighborhood and distribution solar and electric storage, which still fall under the DER terminology. So there's a huge rise in DER. And because of this and recognizing this need, the industry has responded by putting very sophisticated control systems behind them. DER, its growth is probably started at the consumer side, and utilities had to quickly catch up with consumer-driven DER. We see in different parts of the world that there are incentives for consumer to own DER. And many times utilities actually provide incentives to the consumer, particularly in the area of demand response and electric storage. So we're seeing that the rise of DER is being propelled by financial incentives by both regulation and consumer and by utilities. So what are the challenges that come about with having high levels of DER, particularly highly concentrated in certain neighborhoods? We need to have very much more sophisticated understanding of how it will be dispatched, whether it's autonomous or whether it's controlled. How do we understand the consequence of high penetration DER? So we have to take a look at historical reference to the use of DER and how that affects the grid and the growth in certain neighborhoods, particularly those that may have such high penetration of solar rooftop and electric storage that they actually can overwhelm the distribution circuits themselves, particularly the substations. And a little bit later in the talk, I'll be explaining how we bring supply side DER coming from consumers into a wholesale market. I'll be talking a little bit about the impacts on the transmission system as well. So we need to know historically what the use of DER has been on the distribution system, and then start to look at what that high penetration is doing to specific feeders. But the DER itself doesn't have to only provide energy and storage. It can provide other things like frequency management and voltage control and voltage support, and even in some cases, reactive power support. And when you start looking at a potential for high penetration DER, you start to need these other types of services. Some of them could be addressed directly from the utility by installing capacitor banks on the distribution system for reactive power, but also they may have to start installing other types of frequency management, or they have to start looking at load curtailment, which nobody wants. So how do we coerce the DER to behave in a way that is beneficial to the grid? We also need reserve capacity, just like we do in the wholesale market. We need reserves, and that's why electric storage is being heavily sought after right now, and hopefully the price comes down where it becomes available to the average consumer at a reasonable price. Balancing the energy challenges, this has to do with the fact that now you have bidirectional power flow on the distribution system, particularly where you have a microgrid or a very small distribution system. You need to constantly balance out availability, supply with the demand. And then not only within one distribution circuit will you have challenges, but between multiple geographic connected locations that are served by different substations. It's very likely that you'll have a neighborhood that has high penetration solar that's served by multiple substations. So you start to get an imbalance that starts to creep in from one substation to the other. And so we have to look at how do we balance this across the entire network. So it's not just from a substation down to the customer. Now, a study was done a couple of years back by the Australia Energy Market Operator here in Western Australia on the transmission system called the SWIS, this Southwest Interconnect System. And when the study was done, AMO predicted that there's going to be a point in time when DER has reached such a high capacity that there's insufficient load to keep the transmission grid operating. And so there had to be intervening measures taken to help prop up the wholesale market and transmission grid. Those of you who can recall back about 4 years ago in South Australia, the transmission grid collapsed because of a number of things, but we don't want to see the wholesale system collapse. We need to find ways in which we can mitigate that. And so distribution utilities, if they start to adopt these types of DER management systems that I'm talking about, will start to be able to help prevent these types of problems. Now, many of you who have experienced working with utilities or even working on electrical circuits, the results of output from a solar panel have been, you probably have witnessed this. The top graph here is showing the solar panel output and voltage coming from a solar panel, but then about 4 in the afternoon, a bunch of clouds fly over and the output from the solar panel is reduced dramatically, and then the clouds disappear and the system is re-energized. Now this is showing a single unit, but when you have thousands, tens of thousands, maybe even 1 million solar panels, this becomes very problematic for the utility. The upper graph talks about output coming from the solar panel, the lower showing energy production from wind. So many of these types of imbalances are being placed on either distribution system or on the grid. And again, we look for different ways in which we can mitigate those without substantial asset investment. So I've mentioned already that there are a couple challenges that come about from DER. These are the topics on the right here are probably the most common that we see. But the one at the very bottom is the one that's causing most problems around the world for distribution network companies. They're seeing that their revenues are being eroded. They're not delivering power, and the consumers are, providing their own power. But those individuals left connected to the network who depend on the utility will be picking up more and more of the offsetting cost of the utility. And when I was in the United States back in the early 2000s, we started talking about the utility death spiral, because at that time, back in early 2000 and 2005, we actually didn't have a means in which to mitigate this quickly, particularly with the fast pace of installations of solar panels on rooftops. So the growth of the DER-MS, the DERM system, has come about because industry reacted as quickly as it could to provide a solution. Now, I mentioned the fact that we also have cascading effects all the way up to the wholesale market and transmission. And this is kind of a high-level architecture description of all the elements that go into supplying large-scale bulk power down to the customer, from both the wholesale generation market to distribution down ultimately to the consumer. But you see these arrows are actually bidirectional. That means that if we do it right, if we provide a means in which we can send information to the DERs, they can actually support the rest of the grid rather than being a hindrance. So what are the things that we do when, let's say that we want to install a DERM system? What are the things that we expect it to do? Number one, we need to know how to register all the DER assets, their characteristics, their ability to perform functions. Some functions may be limited to only one function, like energy, or it could be only storage, or it could be demand response, or it could be multiples of those. We may actually look at aggregating a number of DER as a group, and that aggregate actually has value. And we see that value being expressed in virtual power plants. So you may have a third party who recruits a number of owners of DER assets, and for financial benefit to the virtual power plant operator, the benefit would be to provide a resource to the utility. And virtual power plants in the past have been primarily demand response and energy, but now VPPs can also provide ancillary services. So it makes a lot of sense to be able to aggregate many of the assets in some sort of portfolio. Then after we identify the assets and register them, we figure out how to ensure that we utilize them in the best manner for optimal performance, not only for the consumer, but for the utility as well. And then lastly, the control mechanism. This is where we actually have a communication infrastructure set in place to control every single unit that participates as a DER. So every DER is registered. We know where its geographic placement is. We know its characteristics, and we know how to send it control signals. Over time, what we've learned with these DERMS platforms is that the end device becomes smarter and smarter. And we find many times that an inverter that we place in front of some sort of DER actually can take a rules-based control system, and we don't have to send it signals second by second, but we can actually set up a rule for the next 5 minutes, and the inverter acts on that rule. So for example, if the inverter witnesses a drop in voltage on the delivery network, that it can react in a certain way. If it sees a frequency going out of band, it can actually provide support. So the inverter can detect things that are occurring in real time, and given based on the rules that has been sent, it can autonomously make corrective actions. So some of you who have worked with the utility know that there are a number of functional systems in the network, in the operations center. At the lowest level is our system protection. The next level above that is our SCADA control. Then above that, our distribution management system. And as we advance that, we call it advanced distribution management system. So it gives us a visual display, a geographic GIS connection, and identification of all the assets. And then above that is the piece that connects to non-utility assets. So everything below DERMS is exclusively a utility asset. But once we go up into the DERMS, we now have not only control of or operational strategy for the utility assets, but also for non-utility owned assets. And overall, the top level band here, overall, this is our advanced grid operations center, which controls multiple substations and our connectivity into the wholesale market. So I've mentioned a couple of the characteristics of a DERMS. On the left, we have customer-owned technologies. Each of them may have a controller. In most cases, a controller is an inverter, but we may have more sophisticated controls if a consumer has multiple technologies like storage, wind, and solar. We may, and if they have demand response as well. So all of those may actually sit behind a microcontroller, and just think of that as a specialized router that connects to all the devices, but expresses itself as a single presence to the DERMS system. On the right-hand side, DERMS also has to understand what the other assets are at its disposal. And some of these assets may be owned by the utility. They may be under contract under certain circumstances. They may be coming from the wholesale transmission system. But DERMS needs to know about all assets that are controllable, and even if they're not controllable, what their characteristic is and their obligation to serve the utility. And it's up to the DERMS to decide how to balance everything across all assets. I mentioned communications. We definitely have to be able to communicate to the DER, and there are certain types of networks that have been put in place. If you have a smart meter program, you will have installed communication infrastructure for smart meter, which you can piggyback on for DERMS management. In some cases and in some countries, smart meters actually can communicate directly to the meter can communicate directly to the DER and control them. Those of you who like really complex architectural drawings, this is one that we've used in the United States. We've actually used it elsewhere, but it kind of depicts the various operating entities on the entire flow of the system. So we have on the left, in the vertical area here, this is items that are within the transmission operations. This area here, which is kind of the mid-level upper left, is all of distribution. And then this section right here, which is the lower mid-level, is all distribution energy resources. And this is our architecture for how we identify the functional components that we can actually control and receive information from, and then figure out how to optimize. And then ultimately at the end, we have the consumer premises. Some of the assets may be consumer assets. Some of the assets on the DER may be utility-owned assets. And then we kind of stratify it here on the right by saying some of these are market-related. There's an economic incentive. Some of them are enterprise-based across the entire distribution utility. Those that are in operation, as I mentioned earlier, in the mission control system. Then we have substation level, field level, and finally, the last piece is the process level, which is what I was referring to earlier as having an intelligent smart inverter. Now, I've mentioned the fact that industry has reacted to a demand that utilities have had, starting from mid-2000s to a bunch of pilots that took place until ultimately many, many mature products came about that have been placed into service and are doing quite well for the utilities, and they're actually managing the operations of the utility DER and consumer-owned DER. So these are the major functions that we see coming from typical DERMS. We talked about DERMS management. Then there's the function of reliability and resiliency. There's the integration to different types of assets. An asset could be an aggregator like a VPP, or it could be a market. Then we have to figure out how to optimize everything, and I'll get into kind of the complexities of optimization in just a minute. But this is probably the single most important part of the characteristic of a DERMS, is being able to optimize everything to minimize disruption, but provide an economic incentive for every participant in the grid. And then the market function, which I'll talk about a little bit later, talking about distribution system operation, which is a DSO. When we look at acquiring a DERMS from a utility's viewpoint, there are many things that we look for in their requirements and the capabilities. I'm not going to go through each one of these, but let's just say that there's a very large laundry list of functional requirements. For those of you who are interested in looking at what the standard requirement mix is, it's been published by the Smart Power Energy Consortium based in the United States. I think it's a list of about 75 different requirements that a DER management system has to fulfill. And it turns out that when I was working with Horizon Power, I actually used that requirements list in our tender, that any bidder who wanted to provide a DERM system for Horizon Power had to fulfill the needs of that requirements list. And because it's become so popular to use that single list, many DERMS providers now have say we abide by the so-called list. You know, the SEPA is called the SEPA list. Now, I talked a little bit about how we implement and look at the registration of DER, and I've talked a little bit about some of the operational requirements. I'm going to get into a little bit more detail at this point. So these are things that we have to be able to do with a DERM system. Not only do we have to manage real-time disturbances and management of all the assets, but we also have to start figuring out how to schedule a day ahead or multiple days ahead the use of an asset. So if you have a consumer like a farmer or an industrial complex who has a rush to get a specific delivery out, and you still want to provide that consumer some financial benefit for participating, you can give them a signal ahead of time that you're going to need their resource at such and such a time. And then that owner, that consumer, can adjust their operational facility accordingly or choose to ignore it and not get the financial benefit. But the DERM system needs to know what those relationships are and those contracts and those agreements, and then they have to implement the strategy that that schedule has set forward. So that's just one of the many things that a DERM system does that's beyond real time. It's looking at things that are going on in the future. So one thing that it can look at is looking at the forecasted weather, anticipating what a cloudy day or a rainy day will do, and we'll schedule certain assets, DER assets, to behave differently under those weather controls. Some things that DERM system can do on the benefit of the wholesale market and even across multiple substations is it can anticipate problems coming from the wholesale market that can be managed by the DER. So things like peak shaving, voltage regulation, get into energy arbitrage, and we start to see the opportunity for using a DSO, kind of a market operator within distribution. Then we see other things like the obvious ones, circuit overload management, volt-var support, and we can even put in spinning reserve. You may find consumers who have their own rotating mass generators that provide some sort of support in that way, and we can commission those. Now I'm going to talk a little bit about the DSO and what role that plays in a DERMS system. The expectation that a mature DERMS product will support distribution system operation, the DSO. But this here is a description of some of the things that we expect in a DSO. We need to be able to contract for energy resources. We need to be able to mitigate disturbances between transmission and the end-use customer. So the distribution system is sort of a freeway or a highway that allows management to take place. Just as I mentioned with forecasting and optimization for DERMS, the market operator also has forecasting, and the DERM system has to be able to link into that forecasting system to be able to optimize across the entire space. Also, what a DSO can do, beyond just looking at wholesale market and retail balancing, it can also provide for means in which a market can exist between participants below the transmission system. So you may have one substation that has a market that consumers can bid into and offer services back and forth between each other. And this becomes very valuable when it may be that you have some consumers that can't afford a solar on their rooftop, a solar panel on the rooftop, but they want to take advantage of solar, and their neighbors all do. Perhaps that consumer who has none can start to buy power directly from the consumers who have solar on their rooftop. So the DERM system has to be capable of managing a market such as this. With that type of market, there's going to be contracts, and so participants who have resources will register their capabilities into a contract, and then that contract has to be managed by the DSO, and the DSO is managed by the DERMS. So the DERMS has to understand how to not only balance power flow, but it has to know how to balance out markets as well. So here I've put a little picture together of where we think a DSO would make sense. And some people who have looked at this diagram have said, well, gosh, that looks a lot like a microgrid, which in fact, it could be a microgrid or it could be a composite of multiple microgrids. But the DSO here in this case is providing reliability to critical infrastructure such as police stations and fire stations or hospitals to ensure that their energy is highly reliable. And so there may be a special market operation just to ensure that that reliability exists. But those entities, the fire stations and so on, have not built their own microgrid. They've actually participated in a DSO. And that's what the DERMS is there to do, is to provide and facilitate the contract relationships as well as moving the power within this subset of the broader grid. You can see as I start to explain this that a DERM system is very, very complex. It has the capabilities of managing at the micro level, like a DSO, as well as across the entire grid and connecting even to the wholesale market. Now, there's a lot of similarities between a utility grid DERMS and a campus microgrid. And so what we've found over time is that microgrid controllers have actually been the originator of the new product mix coming from a vendor called a DERMS. If a microgrid control company can do a really good job balancing all the power within a geographic footprint in a microgrid, then with a few extensions, that microgrid controller can move into the network operations center for utility, and we'll call it a DERMS. And that's what's happened. So the market has evolved coming from the microgrid space into the utility space. So it wouldn't come as a surprise to you as you're listening to this that as we start to see more and more microgrids starting to occur within the network, they then become kind of a virtual DER, if you will. A microgrid can be looked as a black box that to the utility may consume energy, it may provide resources, but more and more the microgrid and multiple microgrids start to behave as DER, and they become very sophisticated. So the question is the DERMS actually capable, the DERM system that goes into the utility, is it actually capable of also providing the microgrid controller aspects, and the utility now has a new market, a new way in which to earn revenue? Can they take their DERMS investment and turn it into a bunch of microgrid controllers? And I was part of a study back about 10 years ago where we looked at a utility in North America that had 85 substations, and we looked at converting every one of those substations into the head end of a microgrid. And it actually made financial sense for the utility to do that, but they had so many years left on their books, on their asset base, that it wasn't practical from a long-term financial investment. All of their assets had not been properly depreciated. But we could actually make a financial case to build a utility from scratch, making each one of the substations as a head to a microgrid. So this is kind of interesting, and we may see this evolve over time across different segments of the world. So this is getting close to recapping some of the materials on the capabilities of a DERMS. We know that there are changes to the utility that we need to cope with. We know that the network is very stable, but we're recognizing new assets are coming on that the utility didn't forecast, and so they're creating additional networking problems. But on the positive side, industry is keeping up with demand, and so as utilities are prepared to embrace this new technology, the industry actually has mature products that can solve some of them. I want to briefly talk about one of the challenges we have once we start to aggregate DER. Many of the aggregates are managed by a third party, not the utility, and they are expressed to the utility as a virtual power plant. But we need to be able to do the same thing with aggregates as we do with the wholesale market. We need to be able to have split-second response. And if you look at the timing buckets across the top. We have 5-second increments going to, or half-second increments going to 2-second increments to 5 minutes, and so on to day ahead. We need to have a system capable of managing schedules on different time scales. So as we aggregate more and more, we need to be able to segment those aggregates and be able to dispatch them according to a timing rule. And those timing rules have to coincide with the market timing rules as well, the market being the wholesale market, the transmission system. So we see that they are, at the wholesale market, there are tariffs already, and there's contracts. We'll see that the same sort of incentives start to appear on the distribution side. We already know the contracts are there for VPPs. As we start to implement a DSO, we'll have contracts within that. But you may find that the regulator actually changes the tariffs for certain types of DER. So if you, and in some cases we've seen that, if you supply power back into the grid, but you're a consumer of power, you may have different cost structures associated to exporting versus importing. So we'll see more and more tariffs appear directly to the consumer. Then the lower section of this graph is the architectural diagram that I showed you earlier, but it just goes out to point out that we need the DERM system to have the ability to schedule in different timescales. So I started talking about the DSO. This is kind of be the last slide on DSOs. It goes to show you that a DSO is an aggregator. In most cases, a DSO is geographically confined. It's very unlikely that a DSO will appear disparate across different substations that there's no, it's not holistic, I'll put it that way. So we see DSOs starting to pop up. They interact directly with the utility distribution system, the prosumers, the consumers who export and import, microgrids, as I mentioned earlier, other types of just plain old consumers who simply want to accept generation resources and buy power. And then you might have third parties who actually install and invest in DER directly. We see that quite a bit happening, particularly on the electric storage side. There are third parties that actually own and operate the electric storage, but they place them into consumers' homes, and they provide a small incentive to the consumer, but their biggest value comes to providing storage to the utility. I don't have time to show you this video. If you want to take a look at it, record this, take a look at the recording here. But this is a video that we did about 3 years ago when I was at Horizon Power. It talks about the DERMS deployment that was being undertaken at the time in Onslow. And the product that we used was one from North America. It's called PICE, P-X-I-S-E. They have a microgrid controller, but actually it is also a DERM system. And if you recall that Smart Energy Power Alliance, the SEPA set of requirements, 75 set of requirements, this company actually fulfilled all of them. And everything that I've mentioned as a requirement to operating DERMS was fulfilled by the PICE system. So one more last architectural diagram. I think I'll just continue moving on. This is coming from one of the energy labs in North America that talks about the architecture of the grid. For those of you who are interested, you can get in touch with me about this. It basically talks about how we're going to measure and manage energy reliability and resiliency across the entire country. So I've mentioned the Swiss and DERMS participating in the Swiss, excuse me, over East. You have the network energy model market, which is the NEM, and just a similar type of approach to solving very large systems like that. Excuse me, I need to take a. So on the right-hand side of this is our traditional systems that we see within the utility. You have energy management system here in the middle. You have distribution management. You may have a DERM system that has been installed. It just connects to a bunch of other units. And then you have a demand response management system over here that accepts a bunch of aggregators. This is kind of where we were, the state of the art, about 5 to 7 years ago. But today, the newer systems, all of this is integrated. So you have your advanced distribution management system that manages all of the assets, and then the DERMS handles the forecasting and market operations, has a sideway connection to distribution management, but a hierarchical management system of all the devices under it. And this is pretty much it in a nutshell. All the assets that may be controlled by the system operator or the network operator is visualized here. You may have some localized control, as I mentioned. You may have autonomous control where you send signals and rules base all the way to the central command system. And that is the utility DERMS. That's what we're all about. So here's a real quick advertisement. In addition to owning General MicroGrids, I also am the chair of the Microgrid Center of Excellence here in Australia. We have about 50 members. It's growing strong, and we're trying to build a new industry here in Australia, and this industry then will take across Asia Pacific and even Indo-Pacific. We are in negotiation with India to develop a mutual partnership. We're working with all the universities here in WA. We'll be working with other universities across East as well. So if you're interested in that, please get a hold of me afterwards. But that is it. Thanks a lot for listening to me. I'm going to turn this back over if there's any questions.
Thank you, Terry. A very interesting topic and informative session. If we have any questions, please, you can ask Terry now. Let me start one question if we get another from others. So you talked about the VPPs, Terry. First of all, I wanted to know what are the main challenges with the VPP, and also the way that VPP sends the signal. Is that sending it to each inverter or DR when we send any set point, or no, we send it to VPP and then the VPP will send it to each asset?
Actually, there's not a lot of challenges with the VPPs. VPPs have arisen because they're a benefit to the utility. And the VPP may have a single characteristic or it may have multiple characteristics. Here in Australia, they typically are just a VPP for energy. In other words, the VPP exposes consumer-owned generation to the utility. But another type of VPP is demand response. We don't see that much here in Australia. We see it in other parts of the world. But this is a way to curtail load under certain circumstances. And it's absolutely essential part of a DERM system in which to balance the power flow. But the VPP itself, it may directly send signals, or it may send rules just the way that a DERM system can. Just a little bit of history. Back 20 years ago, VPPs at the time weren't called VPPs. They were just called aggregators. And all they did was dispatched demand response. In other words, a VPP would negotiate a contract with an industrial plant or a commercial site for that site to receive a signal to turn off their boiler or chiller or the air conditioner. And the signal that they used was a telephone call. So it wasn't very sophisticated in the early days, but it was still had value to the market. But they have evolved over time, and now they're very sophisticated controls. I think that what we're going to see is that as more utilities embrace DERMS and start to implement DERMS, there's going to be less and less a need for a third-party VPP, because a DERM system can do it all.
you.
Terry, I have a question. Just so you mentioned the Pixie software for the distribution. Pikes, yep. Is there any other kinds of, that's for distribution like management, right? And like bars and etc., right?
Yes, it's designed both as a microgrid controller in one instance, but in its full capability, it's a DERM system. There are probably a dozen different DERM systems available today. I know Schneider has a DERM system, S&C has a DERM system, not Schweitzer. I can't think of all. Siemens, they have a DERM system. GE has one. Oracle Utilities has a DERM system. They're popping up because they're high in demand.
Oh, sweet. Yeah. Also, how realistic is the 0.5 seconds for the demand response and for the spinning reserve or a BPP? How realistic is that?
It's not realistic for DERMs. It is very much so for a microgrid controller. And recall that I said, they're pretty much the same type of application. They just have different scales. So a microgrid controller will definitely want to look at half-second type of controls because the distances aren't as great, and we can actually provide an Ethernet connection within a campus on a microgrid.
Okay, right. Thanks.
Yep. Very good questions, though. Thank you.
Do we have any more questions? Thank you, Terry. I think, yeah, we're up to the end of the session. Thank you very much again. And thank you for everyone for joining us today.
My pleasure. Please provide my contact information if anybody wants to follow up with me separately.
Sure, Terry. Thanks a lot. And again, everyone, if we want to, we share this in our YouTube channel, so you get access to the presentation as well. Thank you, everyone.